if you have like sodium, fluorine rich fluids in the system.
Stacia was talking about the mobilized marble on Highway 20.
Yeah, I caught that last part.
Yeah, that's always been so bothersome. But cool.
Did you guys talk about that when you took Nick across Highway 20?
I don't think we stopped there because it's kind of awkward.
Yeah.
Because we were trying to only go to places where people could stop easily, so that not to encourage them to do.
Crossing the road.
Yeah.
So mostly for Stacia and Bob, but maybe all three of you, Stehekin has been a common popular access point for you, or not necessarily? Highway 20 is a much more convenient way for you to get into the backcountry of the Skagit. Nice?
I'd say for this project, in the last 4 years or so, we have been trying to do more mapping down in this area and trying to connect in and link some of the maps between Bob's master's students who work down here.
Yeah.
And then connecting to the north. And this has been a good spot to work out of, and also to hire horse packers to go in and kind of be dropped off for 10, 12 day type trips.
And for me, it was often, I forget, I think the first time I came up here to do geology was probably 1983 or 84.
Yeah.
And we were going up, or I was going up to the Ross Lake Fault Zone, and it's on the west side of the divide between Lake Chelan and the Twist River.
Okay.
Normally, if it was right on the divide, I'd prefer the Twist River.
Yeah.
Because you start at 3,000 feet versus 1,100 feet.
Right.
And you're not fighting, you don't have fewer rattlesnakes to worry about, but for accessing other parts, this is by far best. So it's, I don't know, it's probably 15th time I've taken the ferry up here. I don't know. Seems like a lot.
Yeah.
But over, whatever, 40 years.
40 years.
Cross-cutting looks like it's very young, but then it hits the contact with the biotite schist, paradise, whatever you want to call it, and I think there might be a little shear zone along that, but you can see here's an igneous vein, looks like, and here's the sheet of igneous material that's now nice, fairly homogeneous looking, cut by this. Then you see it up here. See, this thing gets a little folded.
Yeah.
And then their tails, or not, it's not a tail, that's cross-cutting, but you see then this, how many generations of melt are there in here, and how complex it is, and what, so, you know, somebody like Mike here could probably get us 7 dates, and was it $2,000 a date, so.
He gives us a
For you,
discount.
Bob, yeah.
You got the Mike Eddy discount.
Yeah, well, he was calling about it. We've heard that a lot on this trip. When Sarnoff and I have.
Friends and family.
When we were hiking, yeah. We wanted to get that rate. Then I bought him a nice bottle of wine, and he decided to get a date for free.
So, from my point of view, which is rather basic, this was originally sedimentary rock. This was originally a magmatic pluton of some sort, maybe here as well. And then you plunge everything down greater than 20 kilometers depth. That's when all the complications show up, when the thing's down there deep?
Well, these could have intruded at depth.
At depth.
Yeah, so these came from the surface at some point down to 20 kilometers. Is that
Yeah, probably more 30.
Okay.
25.
20 to 30?
Deeper than 20, yeah,
And then they're getting intruded by this stuff.
while they're down there.
Yeah. Well, I mean, what you originally said could be true, but I would suspect that these are getting intruded while it's deep.
Okay.
I think from the bigger scale of the project that we're working on, one of the things that Sarnov is really interested in is when did sediment get incorporated,
Yes.
and when did deformation happen relative to large-scale regional magmatism. And so here we have the sediment, and it's intruded by these orthogneisses, And so what Sarnov can do is look at zircon that were in the sediment. So they would be detrital, so things like you would pick up in a sand or a siltstone today, but they've been on a big journey down to the base of the crust, and figure out what the youngest detrital zircon is in here. And so the sedimentary rock had to be deposited after that. And then he can date the orthogneiss, and we can bracket when the sediment had to go down the hatch. And so between the youngest thing in here and the age of this, it had to go down. And then an outcrop like this is also useful because it has the cross-cutting relationships where, like say up here, I'm going to assume this is an orthogneiss, although I'm not sure. But this darker colored thing was intruded by this lighter colored thing.
Yeah.
They both have the fabric, so we know that they both experience deformation, so we can start to put constraints on that. And then these dikes come through, presumably late. They don't look like they have a fabric to me. And they're cutting everything, so we can bracket when this deformation happened.
Yeah.
So between the age of these rocks and this rock, this fabric developed or was enhanced. And so then we can compare that to when we think magmatism was at its peak. And
then we can also date different parts of the deformation too, where you have the gneissic fabric in that orthogneiss that you can place some of the timing estimates by dating that dike. But then you can see once that dike goes into the metasedimentary rocks above, that dike is deformed and it's kind of doing that boudinage type pattern where it pinches and swells. So we know that there's deformation that's also younger than that dike too. So by dating it, you're kind of getting estimates on different generations of deformation that affected the outcrop.
I love it. Yeah, this is good.
One other thing, we talk about sheets a lot. You hear us, at least informally between us. And so, this is, when you say a sheet, usually in introductory geology, you talk about dikes and sills, right? And then that's fine when you've got horizontal sedimentary rocks. But a lot of the magmas here, like this one you'd call a sill, and that kind of class because it's parallel to the mica schist. But in many cases, you have things that are planar, but they're not really dikes, vertical. So we often use the term sheet because that's a tabular body, so either a dike or a sill could be a sheet. So this sort of shows this sheet-like geometry where it's been folded or deflected, but it's, coming in along the foliation on the schist. So we see this on one scale here, where I probably could, if we stood back, we could probably see 5 sheets, 6 sheets in this outcrop.
Right.
And then the question becomes, we think some of the bodies of what we are sheet-like on the map scale, and sometimes we loosely call those sheets, but they themselves are made up of hundreds of sheets. So, and I think some work I did a while back with some of the 70 million, or 70 million-ish plutons, like the Cardinal Peak pluton that Mike's student Sorov's working on, that was beautifully sheeted on a vertical scale. So I think that's this illustrates it. And again, it's hard, as Stacia mentioned, sometimes it's hard to know. We assume it's sheeted, but we don't always see the boundaries when nature doesn't always cooperate.
Right. Good, Bob.
so it sheets all the way down.
Well, remember that was what we were editing Sarnov's abstract. I wanted sheeted units. He called it one sheet. So
I did
Sheets
notice a
within
lot
sheets.
of sheets got into that abstract. There was a lot. Sheets was repeatedly used.
well, no, it was Mike. Well, I guess it was me. I didn't like the connotation that each unit was one sheet. I mean, I think it's just the way it was worded. So that's why I got into sheeted units. Oh yeah, and the discordant one.
Yeah, it does look like there's kind of high temperature as well as low temperature. A lot of this looks kind of low temperature deformation. It's kind of almost looks over in there, kind of fractured.
Yeah, I think that whole style.
Here.
Well, this is part of, it's probably a large dike-like body, or sheet-like body.
Okay.
And it's a very distinct, I think what makes it important to us is how distinctive it is.
Good.
And it's also been well dated. So the fellow named John Adams, who I think he did his PhD in 1961, was the first to describe this.
Yeah.
And he noted these white plagioclases that you can see, and that Stacia has a sample that can show it, but they're actually filled with, or in the center are these root beer brown sphenes, or what have been renamed, much less a cool name, they've been called titanites more recently.
Okay.
And this, so he mapped this, or describes it in his thesis, and there was something he noted, it's like, or I read that maybe, it's like something they call flecked gneiss. So we started calling it the Flecker because it was such a cool rock, and it's very distinctive.
Yep, keep going.
But what we found is there are dikes of this with this sort of texture from here, from south of here, all the way up to north of Highway 20.
Huh.
And so it's so distinctive, and through dates by Stacia primarily, or maybe entirely, we know that it's a pretty restricted age range of 49.1 or something to 47, about.
I think that's right.
Oh, it's Eocene.
It's
So,
Eocene.
And the other part that's always really interesting that you can see well on the face that we were looking at here is that often are strongly deformed, where those plagioclase rings around the titanite are strung out in that kind of, basically recording the lineation. So it's telling us about that ductile deformation. I mean, as we know, and we've seen in a lot of different places, is quite young and lasting through kind of big pulses of magnetism during the Eocene.
And as Stacia said, it really is more being strung out like pencils. There is a little bit of a foliation. You can see on this face, there's some elongation, but it's much, much less than on that face.
huh.
And so that tends to be the norm, not every place. I don't know how many of these we've seen, 20, 30 over the years. When I first came here with, I showed Roland Tabor and Ralph Haggerut this, they said, oh, it's the bookend porphyry, because I guess Ralph made bookends out, cut a big chunk to make bookends out. But they found it north of a place called Elephant Butte, which is, about halfway between Highway 20 and the Canadian border, or maybe not quite halfway, but
Yeah,
well
it's kinda
north.
Northwest of Sourdough Ridge,
Okay.
Sourdough Mountain, if anyone's done that hike up there.
And that one's been dated. So I think that's the real, there are very few things you can, well, not that many things in the Skagit you can put your hand on, and without having a date, you can say, oh, that's the Flecker.
Yeah.
And so it really holds things together. And again, it's important because it does illustrate the way the rocks are being stretched in during the youngest deformation of the Skagit gneiss complex.
I see.
Because again, these really pretty looking things are overlapping in age with Mike's Golden Horn batholith,
Right.
Cooper Mountain batholith,
Right.
which are largely undeformed.
Well, anybody coming up this road that loves geology, you're going to see this. I mean, it is right there, right on the shoulder. We're looking up lake. This is the head of Lake Chelan in Stehekin area.
I love this outcrop. Skagit complex has so many beautiful rocks, but this really stands out.
Yes.
And as I was telling you, this is one of those outcrops that visitors can clearly access, and you know it when you see it.
Right.
One of the intriguing things about this specific rock is that you have the plagioclases and you have the titanites in there, and you can comment about the deformation, but we don't really understand how this forms petrogenetically. Our understanding of this particular feature needs more work, I think. Would you agree about
Because it's an extensional environment.
Well, no,
No,
I think
like-
just this is, it's kind of, I think what you're getting at, Sarnoff, it's almost like a petrological oddity. Like, why do you have igneous sphene or titanite in the core of what was an igneous plagioclase? So commonly you see that relationship. You see, you say, oh, well, maybe it's replacing the plagioclase, but it actually has a good igneous shape. And interestingly, I've talked to some fellow who worked down, a professor who worked in Baja, and he said there were very similar looking things that are cored by magnetite.
Yeah, I've read about it in other places.
And in
with
Japan, I guess the Japanese are really into them. Japanese geologist, doubt the average Japanese would. But they, some of them have ilmenite, which is another iron, it's a titanium oxide. So there's something, perhaps the state of oxygen is what I've read, but I don't think we know.
So what this map, first let's orient ourselves with this map. So this is the Lake Chelan. So Stehekin should be somewhere right here, and we are sitting somewhere here. And this is the Highway 20 up here. The Ross Lake, the Diablo Lake is over here. And I think I should describe the different units here. So the oldest dated unit within the Skagit is this dashed unit down south in contact with the Cooper Mountain. This is the Ferry Peak orthogneiss, dated to be 76 MA by Jeff Wegner and 79 MA by Erin Shea. So this is the oldest mappable orthogneiss unit down here. It's distinguished by the presence of hornblends, and it's higher in color index compared to rest of the orthogneiss sheets in the Skagit. The next unit that's of slightly younger is the Stehekin orthogneiss right here, and it extends far up north, and it's predominantly 72, 70 MA age range, and it can have older, smaller orthogneiss sheets within itself, but primarily what we have dated is about 70, 72 MA.
Okay.
These two units are more or less homogeneous and can be mapped over a long distance. The unit marked by Z's just to the west of the Stehekin orthogneiss has been described as the heterogeneous orthogneiss unit, and it's heterogeneous because, one, different parts of this belt have given us different ages. It has distinctively more pegmatite units than rest of the Skagit units. Also, this unit, between these two units, the Stehekin orthogneiss and the Western Skagit orthogneiss, lies several small rafts of metasedimentary units that are hosted between these two units. And that is really interesting because as you move south, Erin Shea described a lot of migmatite zones at the southernmost Western Skagit orthogneiss. And that's really interesting, I feel. And then going far east, these units, this unit, big block of unit, is a leuconeiss unit. And it's interesting in composition. It's one of the youngest orthogneiss units within the Skagit. Predominantly we get 60 to 59 MA ages from these leuconeisses. Further up here is the slightly older, but also leuconeiss, is the 64 MA Mount Benzarino orthogneiss. So all of this combined forms the Skagit orthogneiss unit.
Fold the whole thing out. But the reason we're doing this and focusing on, like, say, the Skagit gneiss and the rocks that are to the east of the Iniat Fault, which is running like this, and to the west of the Ross Lake Fault, is because we have a really nice sequence of plutons and orthogneisses that all represent the middle crust during that second flare-up, and then exhumed middle crust during the third Eocene flare-up. And so we have, in this little swath, well, big swath, we have sort of different crustal levels exposed that are all contemporaneous during this period of time that's of interest.
And it sticks out like a sore thumb. There's nothing like that anywhere else on this map.
And I guess the last thing to follow up what Mike brought up, which is a good point. If we take the Entiat Fault, if we ignore the Chumpstick Basin down here, as he has seen, this part of the North Cascades was mostly deformed in the mid-Cretaceous to mid-Cretaceous really, and the Mount Stewart area, Icicle Creek, running this whole band. There's a lot of 90 million year plutons. Some of the evidence is that deformation was over and the rocks were cooling by 80 million years, particularly down near Mount Stewart. And so the idea is this part of the crust, it wasn't inert or dead, but most of the action for the middle flare-up and younger is northeast of the Entiat Fault. And so, as Mike said, that's where we're focusing. So it's in part just that's where the rocks are of that age, and we can actually get at the history better.
And there's no evidence of any single fault that's got 1,000 kilometers of offset on it, which was the thought maybe a generation ago, but it feels like the search is over for that amount of offset on this map or areas to the north.
I guess I would say we think there could be, probably on the Ross Lake Fault, of at least 100 Frost system, because it's not just one fault, it's a whole series, the Hozameen Fault, and then going over to the Ross Lake and the Gabriel Peak shear zone, tectonic belt, whatever you want to call it. That may, I think the estimate we used or concluded it was probably you could document about 130 kilometers of right lateral strike slip.
Yep.
It could have more. The Entiat Fault is the one that's really appealing to a lot of people, that it could have major offset, but the problem becomes you do have the same units on both sides, but where we can really show the age is down here, where it's post 47 million. It gets down younger than, because it deforms the Chumpstick Basin, so it's putting Chumpstick against crystalline rocks. And it gets harder when you go to the northwest to put a big fault up through there. And when the Straight Creek Fault is restored, and for those probably are familiar with this, the Straight Creek and the Fraser River Fault, which is on strike in British Columbia, those have probably on the order of 150 kilometers of right lateral strike slip. So that's a lot, but it offsets, because it has a north-south trend. It offsets the northwest southeast striking fault. So we think we can match things up in British Columbia with faults on the west side of the Fraser River Fault. Unfortunately, this map, we can't see that. But we tried and looked at maps with colleagues who work in Canada, and it's really hard to find this fault on the other side of the Fraser River Fault. And country's rough, who knows, but at least at this point, it's conceptually really nice to have that as a big fault, but we have trouble with doing it.
But we don't have a piercing point for the Entiat Fault that is like older than the Yisu, right? So like,
no, we can say we do have the Swakane and the Pequot on both sides, but that's not a piercing point.
right.
Stacia, where's the first place you laid eyes on this gadget knife?
Ooh, that was with Donna Whitney, 2006.
Oh,
No, 2005.
okay.
And Donna had just gotten a National Science Foundation grant with Bob, as well as Sam Bowering. And she was trying to persuade me to stay on for a PhD, because I had started doing a master's with her
Yeah.
on a project in southeastern British Columbia.
Uh-huh.
And so then we drove from BC over here. And so I first got to see it along Highway 20
Ah,
up in that area.
yeah.
Because she was luring me in with the really nice garnet, aluminosilicate, kyanite, silmonate rocks that are up there.
And here we are at Stehekin, same stuff. Is it more or less a continuous mappable body of Skagit gneiss between Highway 20 and here?
Yes.
Huh.
Yeah, there's a trail that comes off of, Thunder Creek
Yep.
arm
Okay.
up by the Colonial Creek campground on Highway 20.
Mm-hmm.
And there's a trail called, I think, Thunder Arm that goes south from there. And then you can take that and hike all the way down here if you wanted. And that's all through Skagit gneiss. But yeah, down in this area, you just get a lot more of the orthogneiss, which is ortho prefix means that it is a igneous source.
Okay.
And then that igneous rock gets metamorphosed. And so you develop the banding and the foliation that we'll see shortly in some of these outcrops.
This is the, oh yeah, okay.
So you can see it has, that really nice streakiness going across it. That's a pretty strongly deformed and metamorphosed igneous rock.
Originally granitic.
Yes, exactly. Yeah, probably a tonalite in composition. So a lot of these rocks are relatively low in potassium. And so lacking K-feldspar, but a lot of plagioclase, quartz, biotite, sometimes amphibole. Like over here, you can really see what we call quartz ribbons, where quartz really ductily deforms easily and it'll take up a lot of the strain. And I feel like in this little corner, you can see these kind of real thin bands that are the quartz getting strung out. And then you can also see the biotite's almost a bit wispy, and I think it forms what we call kind of a SC fabric, where you have one set that's kind of going up relative at, a 30-degree angle or so. That can tell you a bit about kind of the shear sense indicators in here.
And I think that's an important point to really emphasize is a lot of you, we've talked about before on videos, and you've talked about them a lot, with when was strike slip occurring and when was it right lateral. And so what we're trying to do with these kinematic indicators, as they're so-called, the general topic, kinematic being movement, right, is if we can figure out what they are here, then we can say, but sometime between 71 and 55 million, this area was undergoing right lateral strike slip, this outcrop. And then we try and piece it together. Is this just localized? Maybe they got folded, and maybe it was left, if you have folds, of course, it'll influence it. But the only way to do that, I think, confidently, is by trying to get a lot of localities where we get the movement sense, whether it's dextral or sinistral, and tie that in with the ages and these cross-cutting relations that Sarnoff nicely showed just right back there. So I think that's real important. And I think there are some kinematic indicators here.
Yeah, it showed a nice sinistral fabric, I believe.
I believe so.
Yeah, and kind of overall what we've been finding in this whole area and going kind of a little further south along Lake Chelan is an earlier sinistral sense of shear followed by a dextral. And the dextral seems to be, I think the change is probably in the Eocene in that early part of the history. And that's based a lot on the dating that Sarnov's been doing.
So in terms of Baja, BC, if you tried to make all of the deformation here related to the motion of Baja, BC, which I don't think people have, to be fair, some of our observations are showing that during that magic window that people like Basil Tikoff talk about, where you would have the major right lateral strike slip down to about 55 million, I think, in his interpretation. Here we're seeing sinistral, maybe just at this locality. So I don't want to oversell one locality, but it's not that simple. It's not like this was a pervasive right lateral shear throughout the arc. And So that's interesting. I don't know if we've totally figured that out yet, but what that means.
Go over into that bit of shade.
The little scrap.
Exactly.
Well, Nick, I wanted to add something. Well, when I said that the pegmatite was coming in at 55 and also getting deformed, you commented that it's between the flare-up events. But the thing is, the crust is still hot from the emplacement of magmas previously. The crust is also deep. And all of that influences if you can deform the rock or not. It doesn't necessarily have to happen while the flare-up is going on, but it tells you that the flare-up is so significant that the crust is so hot that you keep deforming between flare-ups.
One of the big questions we had that I think we've made progress on, at least here, is what was driving a high flux event.
Right.
So there's two schools of thought on that. There's either you take crustal material that can melt very easily and you shove it down to the base of the arc and you generate a bunch of melt. And so, boom, you've got a flare up, if you will. The other way to do it would be to change the dip of the subducting slab and increase the thickness of the mantle wedge, which would allow more mantle melt to be produced. And so it's sort of like, well, what follows what? And it gets challenging because if you pump the crust full of magma, it gets hot and it gets weak. And so if you're ever going to thrust stuff down to the base of the arc, that's when you do it. So the question was, do you start with magmatism and then you get crustal rocks thrust to the bottom of the arc? Or do you start with crustal rocks getting thrust to the bottom of the arc and then get a bunch of magmatism? I think we have half that answer now, maybe. I don't know if everyone here would agree with me because we haven't hashed it out yet.
Okay.
But my student, Saurav, has looked at the plutons and using geochemical proxies for crustal thickness, he sees the increase in crustal thickness come late. So it's not like starting with thick crust going to high magmatism, it's high magmatism going to thick crust. And so that would suggest that maybe you're starting with a mantle trigger and generating a thicker crust, either through addition of magma to the crust or through weakening it and allowing stuff to get thrust down. But one of the big tools that we don't have yet, I know Sarnav is like in a couple of weeks going to Washington State University to get some data. And then Saurav, my student, is going to Arizona to get some hafnium isotopic data. And those two data sets will hopefully, fingers crossed, tell us a little bit more about what was melting when. Whether it was mantle, whether it was crust, whether it was sediment, that sort of thing.
Yeah. And we can say too that Jenny Matzel, who was a PhD student with Sam Bowering, who was, I guess, one of the original students to work in this area, she also had a lot of this bulk rock neodymium data that doesn't really show a strong sedimentary signature in the magmas that she worked on too. So that's already kind of supporting what Mike was saying. And yeah, so I think our idea would be, in terms of getting those metasedimentary rocks into the crust, is that likely the magmatism weakened the crust enough that then you could kind of, with the compression of the convergence system, under thrust that forearc into this weakened crust because of the magmatism. So, and that fits with the sediment under thrusting, a lot of it occurring kind of towards the tail end of when the plutons are crystallizing. And yeah.
But I think what's been nice with the combination of all the fieldwork over the years with the geochronologies, we can now show that the zone was moving. Whether it moved continuously, of course, we don't know, but we're showing that it progressively moved. There was progressive strike slip on it, really going from 82 million to 59 million, and perhaps, or probably down to younger than that, 55, based on previous work. So it's I think that's been a kind of thing that's hard to do in fault zones, and because generally you can show, well, it deforms an 80 million year pluton, but it's like we just talked at this outcrop. could be 71, could be 55 and a half, you know, and so we got lucky in some ways, and with a lot of field work and a lot of geochronology, we're able to show that. And so I think that's kind of a neat part of the story, although it's not restricted to the Skagit gneiss.